All right, today we are diving into something that sounds like it's straight out of an alchemist's handbook, turning what looks like totally ordinary dust and rock into pure, solid gold. Now, this isn't magic, not at all. It's actually an incredible story of science, chemistry, and just massive scale engineering. So let's get right into it.
So, here is the big question, the central problem we're trying to solve. You see, we're not talking about those shiny gold nuggets you might picture from the movies. We are talking about microscopic gold particles, literally invisible dust, scattered throughout tons and tons of rock. How on earth do you get that out profitably? To really wrap your head around the challenge, look at this number, 0.5 gram per ton. That means you have to process 1,000 kilograms of solid rock just to get a speck of gold that weighs less than a small paperclip. I mean, can you imagine? Trying to grind all of that rock down with old school methods would cost so much money and use so much energy, you'd go broke before you even started.
So, how do they do it? Well, this is where our hero, heap leaching, makes its grand entrance. You know, compared to that traditional milling, heap leaching needs about 30 to 50% less money up front and uses way, way less electricity. It was the ingenious solution that completely changed the game for mining this low-grade ore.
So, let's get into the nitty-gritty of how this process actually works. The best way to think about it is like building a gigantic open-air chemical factory. And the very first step, the one that sets up everything else for success, is preparing the ore. The ore prep happens in 3 main stages. First up, you have to crush these massive boulders that come straight from the mine. Second, you screen them, basically sifting them to get a nice, consistent particle size. And third, there's this really cool step called agglomeration. This is where you take all that fine dust, mix it with a binder like cement, and roll it into these small, stable little balls. And this last step, well, it's absolutely crucial for solving what I like to call the Goldilocks problem.
But, before we can even think about stacking up that perfectly prepared ore, we have to build the factory itself. And the foundation, it's not just some simple slab of concrete. It's a serious feat of precision engineering, and it's all designed to protect the environment.
Okay, so I just mentioned the Goldilocks problem, and it is so important that we really need to take a closer look. See, the size of those little ore particles has to be absolutely perfect for the chemical solution to do its job. Not too coarse, not too fine, it has to be just right. And here's why that size matters so much. If the ore is too coarse, too chunky, the gold stays trapped deep inside the rock and the solution just can't get to it. But if it's too fine, all that dust turns into a kind of mud and clogs up the whole pile, so the solution can't flow through at all. That's why the 10 to 40 millimeter range is the absolute sweet spot. It's what makes this whole thing work. So we've got our ore perfectly sized. Let's get back to that foundation, the leach pad. And I want to be clear, this is not just a big plastic sheet. It is a massive, high-tech containment system. The best way to picture it is as a carefully engineered, multi-layered sandwich. Let's break down those sandwich layers, starting from the very bottom. It all begins with a super compacted clay base. Then, on top of that, you lay down the key ingredient, a high-density polyethylene liner. That's the main barrier. That's followed by a protective layer, then a drainage layer of crushed rock, and finally, a whole network of pipes to collect the solution. Every single one of those layers is there for one reason: total, absolute containment. And just how good is that liner? Well, its permeability is 10 to the minus 7 centimeters per second. Now, that might sound a bit abstract, but what it means is that liquid moves through this material slower than it would through a solid slab of concrete. For all practical purposes, it is completely leak-proof. Okay, so our factory is built. Now it's time for the main event, the chemistry. And this is not some quick, flashy reaction. No, this is a slow, patient chemical brew that can take months to finish. The magic recipe itself is actually surprisingly simple. A very, very dilute cyanide solution is gently dripped over the entire pile of ore. Oxygen from the air gets in on the reaction, and together they basically coax those solid gold particles to dissolve, turning them into a new compound that's water-soluble. And just like that, that stubborn, solid gold is now flowing freely inside the liquid. Now, in this entire massive operation, there is one single parameter that is more important than any other: the pH level. The solution has to be kept under incredibly tight control in the highly alkaline range of 11 to 12. And listen, this isn't just about making the process work efficiently. This is a matter of life and death.
If that pH level drops below 11, the reaction goes haywire and starts producing lethal hydrogen cyanide gas. That wouldn't just stop the gold extraction, it would be deadly. So controlling the pH is the absolute #1 safety priority. There is zero tolerance for error here. This timeline really goes to show that this whole thing is a game of patience. From the moment they start spraying, it can take 2 full months for the gold recovery rate to even hit its peak. The entire cycle often lasts 3 months or even longer. This is a factory that measures its progress in months, not minutes. So after months of patient waiting, we have finally reached the most exciting moment. It's time to harvest that invisible, dissolved gold and finally turn it into something real and solid. So that gold-rich liquid, which they call the pregnant solution, gets piped over to a special facility called an ADR plant. And here, a 3-step process kicks off. First is absorption, where the solution flows through these big columns packed with activated carbon, and the gold literally sticks to it like a magnet. Second, desorption, where a special chemical wash strips that gold off the carbon, creating a much more concentrated liquid. And finally, recovery, where electrolysis reverses the whole process, turning that dissolved gold back into a solid that plates onto strands of steel wool. That gold-plated steel wool is then taken and smelted down to create this, a doré bar. Now, it's not pure gold just yet. It's an alloy of gold and silver. But this is the final product of our giant open-air factory, ready to be shipped off to a refinery for the last purification step. But wait, getting the gold isn't the end of the story. The final, and you could argue the most important step, is the environmental responsibility of safely cleaning up and closing down the entire site. Modern cleanup is basically a full-on detox for the ore pile. Instead of the old method of just rinsing it with water, which is slow and not very effective, scientists now use active chemical treatments. These are designed to specifically target and neutralize any leftover cyanide, breaking it down into much safer compounds. These modern treatments, along with constant environmental monitoring, make sure the site is left completely safe. And this is the final exam. The environmental rules demand that the final concentration of these cyanide compounds in the water has to be less than 0.2 milligrams per liter. This is the non-negotiable pass-fail grade for a successful cleanup. And just to put that number into perspective for you, that 0.2 milligram per liter standard is often more strict than the regulations for certain heavy metals in the water we drink. Meeting this incredibly high standard is the only way to prove that the site has been closed down safely and responsibly. So, from a simple pile of dust to a bar of gold, heap leaching really shows what is possible when you combine clever chemistry with engineering on a massive scale. It transforms a resource once considered totally worthless into something of incredible value. And, that leaves us with a bigger question to think about. What other materials that we currently just dismiss as waste are out there, just waiting for a new way of thinking to unlock the treasures hidden inside?